So shall we start or should we wait for a little?
Can I ask a quick question? Is my audio quality okay? I just want to make sure I'm connected to the right microphone.
We can hear you okay.
Okay, awesome.
All right, shall we start?
Sounds good.
Okay, so hello everyone. Thanks for tuning in. Welcome back to Physics Meets ML. We are very happy to have Miles Cranmer with us today. Miles is an astrophysicist at Princeton. He's at the moment also doing a research intern at DeepMind. Miles' research aims to accelerate astrophysics with AI. We have already heard a lot about his work from other speakers in this seminar series. For example, his work on symbolic regression from his collaborator Shelley Ho last year. It's wonderful to have Miles speak to us today about his latest work. So please take it away, Miles.
Yeah, thanks so much for having me. So today I want to talk about kind of interpreting deep neural networks for physics. So say we train some neural network on a physical problem, and say that neural network kind of I don't know, it speeds up the problem, or it learns to predict something much better than we have methods for. How can we distill physical insight from that? So that's what I'm going to talk about today. So I'm really interested in general in like artificial intelligence for physics, and I think we can kind of break down the full research process. So maybe we have some model and we want to test that model, so we design an experiment, collect data, reduce the data. And so I think this data reduction, that's where a lot of machine learning happens in kind of like, especially like AI for astrophysics. There's a lot of ML kind of getting in that step. This talk is going to focus more on once we reduce that data, how do we actually extract knowledge from that? So that's what this talk is going to focus on. And I think the other steps would be like, okay, once you have this knowledge, how do you build a kind of comprehensive model and make new predictions? And then you kind of repeat that process. So what I'm going to focus on is something called, oh, by the way, if you have any questions throughout the talk, just feel free to interrupt. I like kind of like interactivity. I like that. So I'm gonna focus on symbolic regression. Symbolic regression is machine learning algorithm. So we want to fit a model to predict some Y given some input X. So most machine learning algorithms, you fit scalar parameters inside a model, but symbolic regression, your basis is analytic equations. So it's the full kind of the space of all potential symbolic expressions. That is the basis of symbolic regression. So again, we want to predict Y given X, but we have this space of analytic equations to explore. So if I see this function here, well, this data set, this curve, if I take a symbolic regression approach, I would say, does this look like a cosine? No. Does this look like sine? Compute the error? No, it doesn't. Does this look like maybe exponent of X? Yes, that's closer. So then what I do is I take the exponent of X and I kind of work on top of that. And I find that exponent of X over 2 is the correct expression. So why do we want to do this? So I think like much of the rules in the natural sciences are accurately described by symbolic regression, symbolic equation. So like this is a physics 101 cheat sheet, and you can see that so many expressions on this page are just simple analytic equations. And these are like very accurate models for the kind of like assumptions made. But so really, I think the question is like, why don't we use this as the space of our machine learning models? Because it's like, it's so much more interpretable, and it's kind of, that's the language of physics. So there's this really interesting article by Eugene Wigner called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So I encourage you to read that. It's a really interesting article. He kind of points out all the interesting connections between different fields of science, like pi appears in the area of a circle, and it also appears in the normalization constant of like a normal distribution. So there's a lot of interesting connections from simple mathematical expressions. We kind of call this a Wagnerian prior. So this is the sense that when you're when you're searching for models, you want to favor simple mathematical expressions. And we know this works for like mechanics, physics, chemistry, because that is the language of those fields. We don't know that this works for other areas, but maybe we just haven't found like a model for those. Okay, so you may be asking, okay, still, like, why do we want to use this as our basis? So these are concise. You find a model that is symbolic, it's a concise expression. You can just glance at that model and see the behavior, and kind of, you can use your intuition of symbolic equations, kind of see potential failures just from glancing at it. One thing we found is like analytic equations may generalize better to out of distribution data than the same kind of neural network fit on the same data for physical problems, which is kind of like, that may be like a really interesting future direction for research, is kind of why that is true. I mean, it seems like it's just, we know that basis works well. And the other thing is, I think once you have a symbolic expression, it can lead to physical insight because it is the same language as existing physical models. So you can kind of see connections. So how can I do symbolic regression? So I think Cindy is so that's like Steve Brunt and Nathan Cutt's package. That is if you have a functional basis, so maybe like polynomials or other expressions, and you want to find an equation that is a sum of those known functional forms. And they also have something for rational functions too. So I think that is the approach you definitely want to take if you know your basis. If you don't know your functional basis, so I have a package called PICER, which I recommend you check it out, and I'll talk a bit about that. And that is a genetic algorithm-based symbolic regression engine that is like, you can explore this hierarchical equation space if you really don't know what the equation is. So the way genetic algorithms kind of work for symbolic regression is you express an equation as a tree. So if I have this equation, x1 times x4 plus cosine of x2 minus 0.3, then I represent this as this binary tree right here. So you can see these are equivalent. And once I do this, I can apply what are called genetic operators. And so in a genetic algorithm, I have different genetic operators, and these could be things like perturb a constant, swap an operator into a different operator, maybe change a variable into a constant, constant into variable. Maybe I like delete a section of the tree, maybe I add a section of the tree. And all of these operators are applied randomly, and it lets me explore the space of equations in a more efficient way than like a brute force search. So it's like it's a bit more efficient than a brute force search. So the algorithm, my package use PICER, the algorithm is called regularized evolution. It's a fairly new type of genetic algorithm. The way it works is you have a population of equations, or like population of individuals in your genetic algorithm. You randomly subsample maybe 10 individuals, so like 10 equations. In that subsample, you find the fittest member, so like the best equation. And then what you do is you mutate that one, and you replace the oldest member of that subset, or sorry, of the entire population. So you breed the fittest member in a subsample, and you kill off the oldest equation. And this is a way of kind of promoting your population to be fitter over time, but it's still random enough so you don't kind of converge too quickly on a local minimum. So you repeat this process over and over. So this is my package called PICER. It has this efficient backend in Julia that I wrote to kind of apply genetic operators and evaluate them very fast on a matrix data set. So I have a Python front end, you can see here. So if I have like a data set of 100 rows, 5 features, and my true equation is maybe 2 times cosine of x3 plus x0 squared minus 2. If this is like my true underlying expression, then what I do is I feed those data sets into Pyser. I say, you're allowed to use this operator, you're allowed to use this operator, and I say how long I want to run it. And then so Pyser will run for a bit, and then eventually it'll display like a list of equations that it found for each. It displays the best equation at each complexity, because with increasing complexity, you can always get a better equation, basically. So you can see it finds this example correctly. What you can also do with Pyser is you can define a custom operator. So if you're working in some subfield and you know there's like some operator that's maybe a bit weird and it's not like a common function, what you can do is you can define a custom operator here, and Pyser will actually compile that function, get the derivative of that function, and kind of put it into the back end, and actually run the genetic algorithm with that. So you can see this expression, so 5 cosine x3 over x0 squared plus 3 minus 2.5. So you can see it actually learns to use that function here. So this is like our special function, and it used that to approximate this component.
So a question on this, could you like put in, say, Legendre polynomials, for instance, or something like that?
Yeah, so any binary operator would work, or a unary operator, and the only requirements are that your function has to be defined on the real line. So if maybe your function doesn't work for negative numbers, what you do is you say that, like, you write a function and you would put like absolute value on x or something, and then you could put it in. Yeah. So you're asking, like, can we use Legendre polynomial as an operator, or can we find them?
Actually, it would be both. This was another question I had in the back of my mind.
Yeah.
As you.
Yeah, like yeah, I think you could, like, you can't find. I mean, if you give it the right operators, I think you could find them.
Okay.
Yeah. Yeah. So I thought I'd just take a quick break for questions, if there's any other questions right now.
I've got a question.
Yeah.
Yeah. So in your genetic algorithm, you start with this tree, and then you have to do these operations. How do you choose a probability distribution over the different operations you can make? I mean, some of them are benign.
That's a really good question.
Go on.
Yeah.
Thanks.
Yeah. Fantastic question. Yeah. So this is a issue with genetic algorithms. Is so Pyser is like, it's kind of unsophisticated. Like, it's very, very efficient, but there's like, you can't take derivatives in function space. Like, you can't define a derivative between like a multiplication and a derivative operator. Like, it's a, like, you swap from a multiplication to a derivative, you get a completely different equation, right? So there's no easy way to kind of explore this space very efficiently and kind of condition these probabilities on your existing equation. So really what you have to do is just use constant probabilities. So you might want to tune these probabilities for each of these operators. And then those are like fixed over your over the course of your run, but they're not conditional probabilities. I think that is a really interesting topic for future research. That I think is kind of like, I think it's a bit unexplored, but I think you could totally do something with like deep learning and kind of condition those probabilities. I think that's super interesting. But yeah, Pyser is just non-conditional, like, it's just constant probabilities for each.
Thanks.
Okay, so yeah, symbolic regression is compact. You get explicit interpretations. It generalizes well to physical problems. But the problem with symbolic regression, and this is a problem with PySer too, is it's bad at high dimensional problems. Like if you put in maybe a data set with like more than 10 features to PySer, it's going to have a really hard time to find the correct equation. So Cindy is better at this because it's a sum of functional forms. So you can actually do you can actually search for these terms efficiently, but genetic algorithms scale really badly with the number of input features and the number of operators. And this is a problem that is hard to get around. So one thing to think about is like deep learning. It's kind of the complement of this. Deep learning is efficient at learning in high dimensional spaces. We know this from like image, like computer vision. We know it's very efficient, but deep learning is uninterpretable, bad at generalization. So it's kind of like the complement of symbolic regression. So the question that we ask is, can we combine both? Can we get the advantages of deep learning, the advantages of symbolic regression, and try to kind of dampen the disadvantages? So this is what our main work that we push is. So the method is it's basically like you train a neural network on your problem, and then you do a post-processing step on that neural network, and you try to extract equations from the internals of the network. So it's kind of like you train a neural network on a problem, and then you study the neural network, and you try to approximate parts of it with symbolic regression. So the method is you create a neural network with separable internal functions, and I'll give some examples of that. You train it, and during training, you try to make the latent spaces sparse. The reason for trying to make the latent spaces sparse is that then you can have these low dimensional representations, and it's easy to approximate with symbolic regression. Because symbolic regression, you want as few input features as possible because it's easier to find the equation. So you want to train your neural network with a sparsity regularization. After training, you can apply symbolic regression to the internals of your deep neural network and try to approximate the internals. And then you compose those expressions together, and you have an analytic equation that is kind of equivalent to your deep neural network. So this is a visualization. If I have this, so this is like my whole deep neural network from this side to this side, and I have split it up into 3 internal neural networks, right? So I have this neural network, this neural network, this neural network. So these kind of feed into this one. So I train these neural networks, and then after training, I isolate this one, and I approximate it with symbolic regression. I isolate this one, approximate it with symbolic regression, and those are easier problems because it's low dimension. And then I can compose those together, and I have done pretty much like high dimensional symbolic regression. So that's basically the trick that we use. So the deep neural network's job is still to predict the targets, but it's to predict the targets while kind of being broken up into small internal functions that operate on low dimensional spaces. So that's the trick. So as an example, if I have a set and I know my functional form is going to be a sum over some representation of every element in the set, what I can do is I write down my deep model like this. So maybe G is like a multi-layer perceptron. I train G, and then what I do is I take symbolic regression and approximate G with it. So in this example, I would have like 2 multi-layer perceptrons. One kind of learns the representation of an element in the set. The other one takes that kind of aggregated representation and some other function, some other data, and it makes a prediction from that. So in this example, I would apply symbolic regression to G and F independently after training them. So that's kind of the main trick. So in our original work, we we started applying this to graph neural networks because they have this internal representation that is like very physical, because you have these internal aggregation steps, which bear resemblance to like classical mechanics. So I'll talk a bit about graph neural networks. So we started by trying to extract force laws from a graph neural network. So if I have this data set of maybe 5 particles dynamically interacting with each other, what I can do is maybe I want to predict the dynamics with the graph neural network. So I learn the dynamics, the graph neural network predicts the acceleration of every particle. And while training this graph neural network, I encourage low dimensionality in the latent spaces, because then I can approximate with symbolic regression. So at the end, once I've trained that network, I try to extract the internal equations it has learned, and I can extract like a known spring law. So we did this with many different systems, so I'll discuss this later. But okay, so the way a graph network works is you represent your data as a graph. So you would have maybe 3, if these are like 3 particles, what I would do is I say they're each a node in my graph. And this is pretty much like analogous to Newtonian mechanics in a lot of ways. So I consider every edge between nodes in my graph, and this is like 2 interacting particles. I take those pairs of nodes, I pass them through this edge model. So that's like my first neural network. And that's kind of like a force law. So that edge model computes like this interaction vector between those nodes. And then what I do is I sum up the messages for like the receiving node in the graph. And that's kind of like a net force. So I take that summed vector, I concatenate that with the original node, and I pass that through this second multi-layer perceptron to compute like the acceleration of my model. So that's kind of like Newton's law, like F equals ma. And the analogies here, like the reason we make this analogy is just to see if we train this graph neural network on a physical problem, and we try to distill a symbolic expression for that graph neural network, is it the same as Newtonian mechanics? And any questions about this? I feel like this one might be a bit tricky to understand.
So I have a quick question. So this approach of trying to encourage lower dimensional representation, do you have to assume the true function have to satisfy certain properties for that to work? For instance, in your mechanics example, if the world is not what we know, that only 3 particles could interact and not 2, then would it totally throw you off with this?
Okay, that's a good question. So, so there's a paper from Jesse Taylor at MIT that actually talks about this kind of aggregation. And basically what they found is that when you have these high dimensional latent spaces, you can actually account for many body interactions. So even though you're explicitly computing like 2 body interactions, because you're summing these high dimensional representations, you can actually do many body interactions at once. So you could, I mean, so I guess that doesn't answer your question, but yeah, I guess like the graph neural network, you can have multi-body interactions even though you're only doing 2. But to answer your question, yes, I think you do make an assumption about the function you want to find based on that low dimensionality assumption. And that's kind of like, you kind of have to at some point, because you're searching the space of high dimensional equations, and there's just too many possibilities. So you do have to make kind of a simplifying assumption at some point and just hope that it works out.
Right.
I think you could do like maybe, I don't know, you could do a search for different architectures and just see which architecture fits your data the best, and then maybe try to approximate that one.
And does the method highly dependent on how you break the network down into small pieces? So
yeah,
it does.
definitely, yeah. Yeah, so I think like a graph network, you're basically making an assumption that you want these messages to be low dimensional in the end. So you're basically making an assumption that the interactions have a simple kind of like low information content representation. So that is an assumption you kind of have to make.
Okay, thank you.
Yeah. Okay, so in the original paper, we tried to see, can we recover like different analytical laws from n-body data sets? So we have like different physical laws. We even have like discontinuous laws. So this is like an if statement force law. So it only turns on if they are, I think it's if they're like greater than 2 distance units away, it'll turn on, but otherwise it turns off. We basically tried to see if we can recover these. We also tried to do it with the Hamiltonian for each of these, with a Hamiltonian neural network. So we actually recover the analytic Hamiltonian for that case. But I won't mention that. I won't go into that in this talk. So we have these like dynamics data sets for all these different potentials. And we try to see if when we train this graph neural network on this dynamics problem, and we try to convert that graph network into an equation, is it the same as the original potential? So this is the training procedure. We have this graph network. We make a prediction of the dynamics. We update the graph network. So we train the network to do this, and we apply this sparsity regularization to the messages so that the messages try to put all the information into as few dimensions as possible. So that's what the gray is showing. So the darker region is like more information. And we can actually, so what we see is that if it's a 2-dimensional problem, what happens is the messages also become 2 dimensions, because that is like the minimal amount of information that's needed to compute the dynamics. So it actually learns like the true force law in the messages. But if we don't know the force law, we can use symbolic regression to extract it. So we get like this rotated version, and then the kind of the second multilayer perceptron rotates it back. So we can recover like the spring law, 1/r squared. We can even extract if statement from the graph network. So we basically wanted to validate this on many simple systems just to make sure our method works before we start applying it to discover like new laws, basically. Any questions so far?
I have a question.
Yeah.
So before you had an architecture which you kind of designed based on Newtonian mechanics.
Yep.
So what happens if you completely change that architecture to like some uneducated guess?
Okay, yeah, that's a good question. So it is like, so a graph network, it is kind of like Newtonian mechanics, but it's not explicitly equal to Newtonian mechanics. Like a graph neural network is, so I think it's a universal function approximator on a graph. Like you could potentially express like any function on a graph. So it's not like exactly equal to Newtonian mechanics. The only similarity that we basically exploit is like these messages, they could be very high dimensional. Newtonian mechanics assumes the dimension is equal to the number of dimensions of space, but you could potentially like have 5-dimensional messages being passed around. So it's like a maybe like a generalized version of Newtonian mechanics. And yeah, I don't know, does that answer your question? But yeah, like it is an assumption that we make. Like, so this is a one message passing step graph network. Other graph networks people use have like multiple rounds of message passing. We only use one message passing step. So that is an assumption we make. Does that answer your question?
So just to be clear, what you're saying is that what you have there is kind of the like any architecture is going to have kind of those steps, and you can just vary like the number of message passing steps and so on. But anything is going to be is going to look like that. Like any architecture is going to look like what you have there.
So like our method, like the general method of converting a neural network into an analytic equation, like that's not just for graph networks. Like you could have other architectures too. The reason we studied it on graph networks is because we kind of know like what they should recover. And we know they're good at like these simple dynamics problems. So that's the reason we kind of test our idea on these. But like, I'll discuss it later, but you can apply this to other architectures, and I'll give some examples of that too. The basic principle is like, if you want to apply symbolic regression to a neural network, you need the latent spaces to be sparse. That's the key point. I mean, I don't know if it'll like, it's obviously like it may not, like it's not a general, like there's no guarantee basically. But the key principle is you want the latent spaces to be sparse. Does that answer?
Yes. Okay. Thank you.
There's a question on chat. I don't know whether you want to get to it or wait until then.
Let me see. Chat. Oh, okay. So how sensitive is it? Oh yeah, so if the underlying force law is like 1 over r to the 1 plus delta, how large must delta be to kind of distinguish it? Okay, so this is a good question. So this is more like a symbolic regression question. Like your neural network should just like fit the, like it'll just fit the correct law, like it'll fit the law that matches the data best. But the symbolic regression step, this is a bit more complicated because when you run symbolic regression, you kind of jointly optimize for complexity and accuracy. So if 1 over r to the 1 plus delta is obviously much more complex than 1 over r. So whatever symbolic regression algorithm you're using, you'll have to make a decision for how much to punish complexity. And if like if delta is very, very small, it might kind of make a decision that the complexity is not worth it. But it's really dependent on kind of what algorithm you're using. Okay, so if you study a system with large n particles, do you need n nodes? Yes, you need n nodes in the graph, but a graph network is invariant to the number of nodes. So you have a graph network, it can work on any size graph. And so the symbolic regression should be the same for any number of n, because you are like where is it? You're basically like you fit this edge model between pairs, and you share weights between every one of these black squares. So it shouldn't matter how many nodes. Like the symbolic regression problem is still going to be the same difficulty. Did you benchmark your method with their NN-based extension? So the method that I'm discussing here could actually be like, it could actually be kind of integrated with their method. So their method discovers a basis using a neural network. And then in that basis, you kind of learn a polynomial. But what the method I'm showing here is you're kind of learning the basis with a symbolic expression. So that's kind of the key difference. So you can't really compare them because they just represent different functions. Like if you have an algorithm that, a simpler example is like, if you know your true equation is a polynomial and you compare a polynomial search code with a genetic algorithm, the polynomial search code is going to win, obviously. If you compare them on a data set that's like more complex than a polynomial, the genetic algorithm is going to win because the polynomial search just can't fit it, right? So there's not really much to gain from benchmarking methods that have completely different bases. So I'll come back to the other questions a bit later. Okay, so a major problem with this method still, so what I've talked about is a way of, even if your data set has a large number of features, you can kind of break it down with the neural network. But if like every node in your graph network has many features, or in general, like if we have many input features, then it's still hard to use this method. Like genetic algorithm-based symbolic regression is going to scale order n to the n with n features. So this is a problem that we've been struggling with a lot. We have this new algorithm that we've kind of created to help solve this problem. We call it a disentangled sparsity network. So on the left is a regular multi-layer perceptron. This is the input layer. So these are like your input features. And then this is the output layer of the multi-layer perceptron. You can equivalently write this down as basically a separate multi-layer perceptron for every output feature. So if I have two output features, I could write down one multi-layer perceptron for each output feature. And when I do this, then what I can do is I can give different inputs to each multi-layer perceptron. And what I can then do is I can mask those inputs. So I can say, this output feature explicitly only depends on this feature and this feature. And I can say this output feature explicitly only depends on this input feature and this input feature. And the reason for doing this is, like, once you've kind of eliminated the potential dependencies of this output feature, it's much easier to interpret that mapping. So actually, I'll just show this. So like, if we're trying to interpret a neural network in some larger model, what we can do with this method is basically enforce that every latent feature in the neural network has to depend on as few input features as possible. So you can see if this latent feature 0, if this is like the input mask, you can see it only depends on 3 input features. And that is a much easier symbolic regression problem. So it's kind of like, it's a way of, like, even if your latent features are sparse, this gives you a way of making it even easier for the symbolic regression algorithm and making the dependencies sparse. So you can make the latent features sparse. This helps you make the dependencies sparse in your neural network. And that makes the symbolic regression algorithm, like, that makes the problem much easier, actually. So that's like our new architecture that we've kind of developed. So that was published in the Sparsity workshop, but we're gonna create like a larger work soon to help kind of explain the key ideas more. So basically, like, if I'm trying to approximate symbolic regression in some deep network, if I break the problem down into this simple mapping, like there's only 2 inputs now and 1 output, that is much easier for symbolic regression. Whereas before, I would have 4 input features, and that's much harder. So that's the key idea. So in the next part of the talk, I just want to discuss like applications of this idea. So we've demonstrated the idea can rediscover concepts we know about. Can we discover something new? So the very first example we tried, this was for our original paper, is can we predict the dark matter overdensity, the dark matter excess in a region of a cosmology simulation? with an analytic equation using the surrounding matter. So it's kind of like, can we learn the correlation of the dark matter excess in a region with the surrounding matter? So what we do is we have this data set of what are called dark matter halos. It's like a blob of dark matter. We treat each of those like a node in a graph, and we try to use the neighboring nodes to inform the properties of that dark matter. So this is useful for things like studying bias in cosmology. So what we do is we turn this into a graph, shove it into a graph neural network, and try to predict the dark matter overdensity with the graph network, while encouraging this low dimensionality representation. And then what we do is we fit symbolic regression to each MLP in that graph network, and we can turn this into a simple equation that we can interpret. So in this equation, M is the mass of MJ is the mass of the surrounding halos, Rij is the distance to surrounding halos, and Mi is the mass of the center halo. And basically what this says is, so the overdensity is correlated with the mass of the surrounding halos, and this dependence falls off with some function of distance, and it's inversely correlated to the mass of the center halo. And well, this equation is like, it's pretty simple, and it's not it's not an exact equation, obviously. It's a correlation that we found, but the key thing to notice is, like, we're actually discussing what a neural network has learned. And that's what this method lets you do. It lets you have a discussion about what a neural network has learned. And we can't really do that with a black box deep neural network. So that's the key point about this. So yeah, so the other thing we wanted to try is, like, so we have this equation. How does it generalize compared to the neural network it's trained on? So the graph network, if we train it on only the lighter dark matter halos, does it generalize to the heavier dark matter halos? And we did the same thing for the symbolic regression. So you train that network, you approximate it with symbolic regression, and then you see which generalizes better to the heavier dark matter halos. So the graph network, 0.06 on the training set, 0.14 on the test set. So the heavier halos, it generalizes pretty poorly. But the symbolic expression, 0.08 on the training set. So it's like, it's worse on the training set, but it gets 0.09 on that heavier halo data set. So it definitely seems like sometimes if you express your model in a symbolic form, it might generalize to out of distribution data because it's a good prior for the space of functions. So in other applications, one thing we wanted to try to do is see if we can do better void cosmology with this model. So a void, a cosmic void, is like, it's this region in the universe that is kind of devoid of matter. So these dark matter halos, and then there's these voids of dark matter. So there's just not much in there. And something that people have started to do in recent years is see, can we use these voids to measure properties of the universe? So we wanted to see if we can find better ways of doing this, better ways of doing void cosmology with this learned implementation. So the problem is basically predict this cosmological constant by learning two functions. So one function is a representation of the original void. So the void might be described by, like, the radius of the void, the shape of the void, like the ellipticity, other properties. So we wanted to see if we can find a good way of representing a void such that this other function can kind of make a better prediction for the parameters of the universe. So this is co-led with Christina. It was published in the SimDL workshop. And I won't talk about this, but basically we found this simple analytic expression. And basically what it says is the optimal observable for a cosmic void is basically like a polynomial in the radius times the ellipticity, and then plus these other terms of radius and like density. So what people have used so far for doing void cosmology is just the radius. So you basically you find the radius of a void, you compute a histogram over the universe of basically like the number of voids at each radius, and that can predict you can use that to kind of make predictions about the parameters of the universe. So this is basically saying instead of radius, we should use this equation to kind of represent a void and take a histogram of this. So take a histogram of voids with this number over the universe, and that can help us make better inferences about the cosmological parameters. So that was a cool recent paper with Christina, and we're doing more work on that. Another cool example is, so this is work led by Pablo and Niall. This is basically like a similar idea to the original graph network that I showed earlier. You want to predict the dynamics of a system with a graph network. However, in this case, they are working with the solar system data. So you give a graph network the solar system, and you try to predict the acceleration of every planet and every moon in the solar system. So what's cool about this approach that's different from the original paper is they don't give their graph network the mass of every planet and every moon. They don't tell the graph network what the mass is of planets. And obviously you need the mass to solve the dynamics of the solar system. So what they do is they let the graph network learn properties for every planet and moon such that it can compute their dynamics. So they let it learn a scalar quantity for every planet and every moon such that the graph network can predict the dynamics of the system. And so what they found, so we published this in the SimDL workshop. So what we found is like, it can actually find Newton's law of gravity, and it can find the masses. So there's a degeneracy in the mass definition. So you basically have to say the sun's scalar is 1. Whatever that scalar represents, the sun scalar is 1. Find the other scalars. And so we basically found like you can find a lot of the masses actually reasonably well. So these are like Earth mass is okay, Jupiter mass. These are like other moons. And again, like this graph framework doesn't even know Newton's law. Like it's bootstrapping Newton's law and mass at the same time, right? So I think this is like a really cool application of these symbolic regression graph network ideas. The planets where it didn't do a great job is where that planet does not have a moon in the data set. And that's because like you can't really measure the mass without a moon around it, right? So yeah, I think this was like a really cool application of this idea. And I think this is also something cool for the future is if we have this dynamical system and we don't know what properties characterize different objects in the dynamical system, can we bootstrap scalar quantities for each object and learn the dynamics law? I think that's like such a cool idea that could have like many useful applications. So I was really excited about this project with them. Okay, so just to conclude, I wanted to talk about the applications. Now, just to conclude, the main idea of our approach is you want to, you create a deep neural network, you train it on your data set, while sparsifying the latent spaces. Then what you do is you approximate the internal components of the neural network with symbolic regression. And you can compose those expressions together. And this is a way of turning a deep neural network into an equation that you can then stare at as a physicist and get physical insight. And it potentially gives you like better generalization too. So one thing I'll just say is sometimes people ask us like, why not straight symbolic regression? And you definitely could do this. Like you could do the whole thing with symbolic regression. But it scales much worse. So say we want to find like two functions at once. We want to find the function for y and we want to find the function for z. So if we did straight symbolic regression and we consider 10 to the 9 equations for this and 10 to the 9 equations for yi, that gives us 10 to the 18 equations total that we have to consider, right? Because we're considering the product of the combinations. But if we do them separately, like we train a neural network first and then isolate the components, fit it separately, then there's only 2 times 10 to the 9 possibilities. So it scales much better if you do this mixed deep learning and then post-process with symbolic regression approach. It scales much better. Yeah, that's my talk. Thanks again for having me. Happy to take questions.
Hi, can I take a quick question?
Yeah.
Yeah. First of all, very nice presentation. Thank you. I just have a question because I'm relatively new to symbolic regression, but I wanted to ask you, you still need to use some kind of a cost function or a loss function in your optimization, right?
Yeah, for the deep learning part, you mean?
Yes. Yes,
yeah,
yes.
For the deep learning part, you do have to you have to model a prediction problem. So yes. For the dynamical systems, you predict the acceleration.
Mm-hmm.
Yeah.
And this is another question, but it's a hypothetical one. Do you think that having constraints on your loss function would also improve any physical interpretation in the post-processing?
So what kind of constraints do you mean? Like symmetry constraints, like
example,
energy conservation stuff?
For example, yes.
Yeah, like I definitely think it would. That would, yeah, I think it would definitely help if you're trying to model a physical system. Yeah.
Yes. Okay. Thank you very much again.
Yeah. Thanks.
I have a question on scales. So
on sorry, what?
On scales. So scales in the
yeah.
problem in the data. So it obviously, like, if you're thinking about spring laws, right, you can fit things nicely about trajectories. But if you're thinking about, 1/r kind of things, things become different. Yeah, can you comment a little bit on, because that can pose a lot of problems.
Yeah, totally. Yeah, that's a great question. So, so if you think about it, a multi-layer perceptron, if it's finite sized, it can never fit 1/r because you have this singularity at 0. And when you train a neural network, there's all kind of implicit regularizations. Like your batch size is a regularization on the L2 norm of the neural network. Yeah, like having small mini batches is an implicit regularization. Often you use weight decay. So you're kind of minimizing the L2 norm of the neural network, but to model a singularity, you need an infinite L2 norm, right? Like, sorry, not an L2 norm, Lipschitz constant. Yeah. Well, the L2 norm of the neural network is related to the Lipschitz constant of the learned function. But basically, yeah, the neural network is going to struggle to learn 1/r. So definitely, if your function has, like, if you know a priori that your function is going to have really nasty scaling, it might be better to predict like the logarithm of the output or something. for the deep network. But once you get to the symbolic stage, it's actually not that bad. Like symbolic regression, because you're not doing gradient descent, you're just kind of randomly walking around in the space. The scale doesn't matter that much. It matters for your initialization of the constants in your equation. But once you get to a kind of reasonable equation, you can kind of walk around the space and it doesn't affect it as much.
I see. So basically the first part, fitting the deep neural network, that's the hard part to get.
Yeah, yeah, totally. Because like the symbolic regression stage, the algorithm that Peiser uses, it's just accepting, it just finds the fittest function. So even if the loss is, I don't know, if the loss goes from like 10 to the 9 to 1, it's just, it doesn't really care. It just picks the fittest function in your subsample and it moves on. So it doesn't really care about step size or anything. So it's a bit better for scale. Yeah.
Thanks.
So yeah, thanks, Miles, for the great talk. So you mentioned this work that you use the nearby meta distributions to predict the diameter distribution. And then you also talk about how you could use the local information of nearby voids to sort of do better in finding this fitting. Suppose our goal is to develop an algorithm to identify voids from the data. Would this method work? Probably not, because it's highly non-local. Compared with the other questions.
For the void problem, it's actually, we don't actually have edges in the graph. It's a, it's kind of like a set. So this is a set of all voids, and we just sum a representation or something. Or we take a mean of the representation, or like a histogram of the representation. So there's no, we don't imply local connectivity, actually. It's just a aggregation over the universe of some void property.
I see.
So if you want to do like void finding with this,
yeah.
So you couldn't use like the exact same algorithm. You would have to actually create some deep model that you would train to identify voids or something. And I'm not sure exactly how you would do that, but I'm sure there's a way. Like you could set up a graph neural network to, I don't know, classify like a region as having a void or not. I'm sure there's a way. And then you would fit the symbolic regression to that after.
Right. Right. So the usual problem is that it's somewhat sensitive to how you move things a little bit around. So what you call a void, if you perturb your meta distribution a bit, it would seem to open up that loop. So so some stable mechanism would be very useful to identify such objects.
Yeah. Yeah, right. And definitely, I think the really nice part about working with deep learning for the first step is there's so many different ways you can impose constraints on the deep network. Like there's a lot of different ways you can get translational invariance in neural networks. Like a CNN gives you translational equivariance. So you can kind of use the same principle in a graph network, maybe. Like maybe in the graph network, you don't give position as a node feature. And then your network's translationally equivariant. So you can kind of impose those conditions on the graph network, and then you get those for free later when you do the symbolic regression. It's definitely like it's much harder to impose those constraints on the symbolic regression, just because that's like such a harder problem to optimize. Yeah.
Great. So I saw that there are some questions on chat. Maybe you can get to them if you have time. And if anybody has questions, feel free to ask Miles.
Okay, so question. Oh yeah, sorry.
Can I ask a quick question? Sorry. Yeah. So this is going back to the very beginning of your talk with Peiser. I'm curious about the fitness function for the genetic algorithm and how it encodes this so-called Wagnerian prior. Does it price in the complexity of the expression, or do you do that at some other stage?
Great question. So you can do that. It's called parsimony. And what you do is you count the number of nodes in your tree. So if this is my tree, I say like 1, 2, 3, 4, 5, 6, 7, 8 nodes. So that's the complexity of this equation. And that is like, it's kind of like an arbitrary prior on complexity. So there's different arguments you could make for like, what is complexity? How do we define complexity? But that's the choice Peiser makes, is complexity is the number of nodes in the tree. And for the fitness function, you could have that. So there's a parameter called parsimony, and that's basically like it's a multiplicative constant against the number of the complexity, and it adds to the loss function. So it'd be like mean squared error plus parsimony times complexity. But what I actually do most of the time is I turn parsimony off. So I say like, during the mutation steps, it can find any complexity it wants, but I limit the max size. So I say, if you get to this max size, then you can't add nodes anymore. So there's kind of like only one direction it can go. And at the very end of training, what Peiser gives you is a list of equations at each complexity. So it gives you the best equation for 1 node, the best equation for 2 nodes, like cosine of x, for 3 nodes. So this is called the Pareto curve. It's a curve of complexity on the x-axis and accuracy on the y-axis, and it goes out to infinity, right? Like you keep adding complexity, you can always find a better expression because you can always add constants, right? Mm-hmm. So what you have to do is make a choice about which equation along that curve I pick. And so the usual strategy that was done in like the major.
What's the name of the curve? What is the name of the curve that you mentioned?
Let me write it in chat. Pareto. So if you go back to the, this is my favorite paper of all time. It's Hod and Lipson, 2009. It's like something finding natural laws from data. The strategy they use and a lot of other people use is you look for a cliff on that curve. So there might be like a drop, and that basically means you increase complexity by 1, and then you find a much better equation. Mm-hmm. And that's usually indicates that is like the true equation. And maybe the other ones are just like fitting noise or something. Right. So that's the strategy. So Peiser has that. If you look in the output data frame, there's like a score column, and that's basically like how much is the drop. So you could use that. You could use like a joint optimization, like I want this accuracy, and then I find the biggest cliff after that threshold. But there's not like a lot of rigor behind it, obviously. So it's kind of something you make a decision about. And I think there's other nice strategies. I forget the name. It's like Bayesian scientist. It was published in Science. I forget the author's name, but they have this really interesting strategy where instead of simply counting the number of nodes in the equation, what they actually do is they have a prior on equation space based on existing equations. So they say these are existing equations in physics, and they define a prior based on those, and they apply that prior to the discovered equations and kind of say like, this equation is similar to existing equations, therefore it's more likely. I think that's another approach that's interesting.
Yeah, very interesting. Well, thanks very much.
Oh yeah, Tyler Josephson found it. Thanks. Yeah.
Hey, Miles. Thanks. Great talk. I have a quick question about implementation of the disentangled sparsity network. So question is it done by composition or is it done as a genetic operator, the partitioning of the dimensionality into sparse networks?
So that's a great question. So what we actually do is we fix the number of multilayer perceptrons before. So you would kind of define, maybe your output layer has like 10 features. That means you have 10 multilayer perceptrons. And you can vectorize this efficiently by basically adding another dimension to your multilayer perceptrons. So it's like it's kind of like a 3D multi-layer perceptron. And when you train it, you encourage sparsity on this input layer, and we also encourage sparsity on the output layer. And what that does over time is you can eliminate MLPs.
I think I missed that. So you're learning the sparsity masks.
Yeah.
Okay, got it.
Yeah, sorry. Yeah, like you can see that even there's some non-sparse components, and it's probably like we just didn't train long enough, or maybe we should threshold more. But this is like a learned mask on the Jacobian matrix. Yeah, and that's basically like the principle. Like we want a sparse Jacobian matrix for every function in our neural network, because then it's easier to interpret. Like I can stare at this latent feature, and it only depends on 3 features. So it's much easier to kind of identify what that function is. And yeah, if you check out Picer, definitely let me know if you have any issues with it. I'm happy to help. Yeah, and I'm happy to take questions via email too.
Are there further questions for Miles? Yeah.
Sure. Hi, this is Federico. I asked this in chat, but I was curious, what happens if you run the genetic algorithm step to obtain the symbolic expression multiple times after you've trained the neural network, and then you treat that as an ensemble, like however, and you just use that to do uncertainty estimation, because I presume you get different symbolic expressions each time. Is that
that's a really
calibrated
nice
in any
idea.
way?
No, but I think that's a super interesting direction to explore. So Picer actually, it has an export feature. So you can export to PyTorch or JAX, and then you can take that expression and kind of put it back in your model, and kind of like, you could like iteratively like improve on that equation. Like, so you learn, find the expression, you add that expression to a neural network, learn the neural network again, and kind of repeat. You could do that, or you could do something like, yeah, you could do the other thing you could propose, which is you find different equations and you kind of have an ensemble. I think that would be interesting too.
That should be really quick to try.
Yeah, I think that's super interesting. Yeah, I would also check out the Bayesian machine scientist. I think they actually learn like a posterior over equations. And I think then you can like marginalize in equation space, which would be interesting. If you want to check out that paper too. Yeah.
Yeah. So any further questions for Miles? If not, let's thanks Miles again for a great talk.
Great talk, Miles.
Thank you, Miles.
Thanks a lot for having me.
Yeah, thanks a lot.